1, right? Okay, so we have a formula for our AI. It's a little bit complicated. We have a much simpler formula for BI in this very special case. So let's actually go to MATLAB and see how that works. All right, so let's start. How many elements would you like us to solve with? Just give me a number.
5.
5. Oh, nice. Okay, and I'm going to do something pretty weird. I'm going to, I mean, if we have 5 elements, then we have 4 nodes between 0 and 1, right? Excluding 0 and 1 themselves. So I'm going to do a rand of an element minus 1. Oh, no. Okay, that's going to give us 4 random numbers. Okay. Okay, and I'm going to be sort them. Let's see, x equal to sort them, and x equal to 0, x 1. Okay, so that'll be my elements. They are, well, their size is as random as you can get. All right, let's see how finite element is able to solve the equation with these very random and few elements. So my matrix is going to be how big? How big is my matrix going to be? Let's go back to where we derived our matrix, right? How big do we have a matrix? Or how many unknowns do we have? How many equations do we have?
N minus 1, so 4.
Yes, we have n minus 1 equations and n minus 1 unknowns, because although we have 6 points and 6 basis functions, 2 of them is determined by the boundary condition to be 0, right? So we have n elements minus 1. And we know that we're going to keep these 3 zeros here and these three zeros here, and only fill the diagonal terms. So let's fill out first of all the diagonal term. 1 to n element minus 1. Okay, and the a of I is going to be equal to, let's go to here, it's going to be the summation over 2 elements. Oh, and I forget to actually integrate them. Sorry. If you integrate this constant number over the domain from x minus 1 to x, what do you get? So let's actually do a little bit more derivation. Okay. Sometimes my pen doesn't work anymore. Okay. Weird. Okay, so if you integrate this term out, what do you get? You get 1 over xi minus xi minus 1 squared, but you get multiplied by the length of this domain, right? So that kind of cancels with one of these xi minus 1. So you just get 1 over xi minus xi minus 1. Right, so essentially in the code, what you get is 1 over x of I plus 1 minus x of, well, let me do it a little bit differently. So let me actually build actually a big matrix, and then let's fill out, and let's get rid of the first row, first column, last row, last column. Otherwise, the indexing is a little bit weird because we are going to be using a different indexing from before. So the loop, we are going to going from 2 to n elements. Actually, we are going to be going from 2 to n elements. Okay, so that's n elements minus 1 items. We are only filling out the middle portion of the matrix. So A of II is going to be 1 over xi minus xi minus 1. So that's the first that's the first integral, right? Work. And the second is 1 divided by xi plus 1 minus xi. So that's the second portion of the integral. So my A, let's examine it. I have filled out these 4 numbers in the diagonal. All right, make sense? Okay, I have to also fill out the 3 upper diagonals and 3 lower diagonals. So let's do the same loop again. I and I plus 1 should be equal to what? It's actually, let's go back to the derivation again. Also, this minus squared thing is also a constant. The integrand is a constant. It doesn't depend on x, right? So multiply that out. We also get one of these squares canceled away. It's going to be a negative number, but it's 1 over xi minus 1. So let's actually, instead of I minus 1, we do this. So 1 divided by xi minus xi minus 1. All right. And then if you look carefully at this, you're going to see if instead of I equal to j plus 1, if you flip them over, okay, the matrix is the same. So basically, it doesn't matter if I mean it's pretty clear from even the definition of aij here, right? If you switch if you switch I and j, the value of this integral doesn't change. So it's a symmetric matrix. That means we can set I minus 1 and I to be the same value. All right. Is it clear what we are doing here? Right, so we have filled out also the upper and lower diagonals, and we only need to, we only actually need from the second one to the second last one. So that's what our matrix needs to be.